So that gets us ready then for a second guess. So again, we've got a better guess. We started with 460 as our first guess at T2. We didn't know for sure. Better guess at T2 would be 181 according to our calculations. So let's see where that leads us. So what does that do for us? Well, again, what the heck are we trying to do? We'll go back to the roadmap. What we're trying to do is we're trying to take a guess for T2, use that guess for T2 to find T average. That gives us C sub P average, and then plug C sub P average into this expression, solve for T2, and repeat until we start getting the same number over and over again. I bet we're going to be very close this time. This is what we call convergence, when we get the same number over and over again. And I bet we're going to be very close this time. So if T2 is equal to 181 degrees Fahrenheit, then with T1 being 540 degrees Fahrenheit, T average is going to be on the order of, so this is, oh, I should have just left that, 181 plus 540 divided by 2, 181 plus 540 equals, divided by 2, 360.5. So roughly 360 degrees Fahrenheit, 361 degrees Fahrenheit. Now, that will give us, again, what are we trying to do? Well, I need C sub P average now. Sorry, I got a phone cord. My phone was about to die, so I've got a cord in the way now. C sub P average, then, if T average is 360, I mean C sub P average, then you hear pop. Make sure I get this on the screen. So I don't have a row for 360, but I do have a row for 300 and 400. I could interpolate between 0.245 and 0.243 for 360. I'm going to bet it's going to be real close to 0.244. You guys okay with that? If I say 0.244 is about what C sub P would be at 360. Okay? Now, if I've got time, if I'm not trying to do this quickly, if I'm doing it on a homework problem, I'm going to interpolate that and try to get a really good value here. But I think we can say this is 0.244 BTUs for pound mass Rankine. Right? So dropped a little bit from where we were up there. And then what do we do with that? Well, we plug this in here. Right? So the only thing, notice the only thing that's changed here is this one number. So if you're using a big fancy calculator where you can put this all in one line, the only thing you have to change is this one number now. Right? Recalculate everything else, or there's some simplification you can do, simplify all the constants. I just have a simple calculator here because this is what shows up good on the calculator, so let's just do this. So it's 12 divided by 16, the natural log, so that's this quantity, and then multiply by this R value of 0.06855. And then I'm going to divide by my new C sub P, 0.244. Again, all I've done is I'm taking this expression right here. The only thing that's changed is this is now 0.244 because I've got a better guess at T2. So I'm going to take e to the power of all this stuff and multiply that to 1,000 Rankine. That's T1 in Rankines. So if that's the case, and that tells me then that T2 is 636 roughly Rankines, or in Fahrenheit, minus 460, 176-ish, give or take, degrees Fahrenheit. So that tells me I'm probably done. There's probably not a whole lot more I can do, because if we go one more, if we try to go one more time through the loop, right? So let's say if T2 then is actually equal to 176 degrees Fahrenheit, that's a better guess, with T1 of 540 degrees Fahrenheit, that means T average, right? So if I add to this 540 and divide by 2, T average is going to be 358 degrees Fahrenheit. And we're going to find, if we go back to the table and look up C sub P average again, the best we're going to do is 0.244 BTUs per pound mass Rankine. And again, you could interpolate at 358 what C sub p would be between 300 and 400. You're going to get very close to this value, and that tells us that we're going to get T2 equals at about 636 Rankine, because I would just plug 244 back in here again, get the same T2. That's when we know we're done. Okay. Well, are we done? Well, I don't know. What are we trying to find? We're trying to find V2. This is not V2, this is T2. How does that help us? Steve, what the heck are we doing? Remember, we said we're going to use the first law to try to find V2. We said I know T1, that means I should know H1. Now I know T2, so I can use that to find H2. V2 now is my only unknown, so I still have to solve this expression. So I got to go back and solve the first law. Now, what page am I on? This is 5. So now I do need to solve the first law equation for V2. So back to the first law, solving the first law for V2. V2 is going to equal square root of 2 times stuff, 2 times, so solve this for V2. 2 times, it's going to be quantity H1 minus H2 plus V1 squared over 2. Which I would suggest V2, we've found a good value for C sub p, let's put it to work. So it's going to be C sub p average times T1 minus T2 plus V1 squared over 2. Okay? Alright, let's start plugging numbers in, shall we? V2 is equal to square root of 2 times, and I'm going to use brackets in here. I have parentheses inside parentheses, and I'll have more parentheses, so I'm just going to use brackets. We said C sub p average, we settle on a value of 0.244, so 0.244 BTUs per pound mass Rankine. I'm going to multiply that by T1. We said it was 1,000, and T2 minus T2 we said we agreed on a value of 636. Those are both Rankines. Now before I add this V1 squared over 2 in here, let's talk about units. What units would you like here? Well, for V2 I'd like what? I'd like feet per second. The square root of BTUs per pound mass is not feet per second. So we have to figure out how do we get this to an appropriate unit. Well, in the back of your text, I always have to double check this. It's about 25,000. It would actually give this value to you. Find it quickly. Yeah. So this text, as I said, is really nice. They normally, yeah, right here it is. 1 BTU per pound mass is 25,037 feet squared per second squared. I always remember it's 25,000. That would get me in the ballpark. I always have to look up those last 2 digits. 25,037 feet squared per second squared for every 1 BTU per pound mass. That's not a value you find very often, but this text is very nice. They give it to you. So we'll go ahead and use it. That's okay. Plus V1. What was V1? Back here at the givens. 200 feet per second. That's going to get squared and divided by 2. And brackets around the whole thing, because the whole thing gets multiplied by 2, and then the whole thing gets squared. Let's see how we do here, okay? Alright, so what do I want to do first? I'm going to do, let's just break it up. So I'm going to say 0.244 times 1,000 minus 636, close parentheses, and multiply by 25,037. So that's this first term. So V2 is going to equal the square root of 2 times this first term. This guy here is 2,222,23,000. And we'll say roughly 700 feet squared per second squared. plus this guy. Now this is just going to be 200 squared divided by 2 is going to be like 20,000. So probably insignificant. That's feet squared per second squared. 2 times that sum. So add to this 2,223,700. And multiply by 2. And square root. That seems really high to me. That seems way too high to me. Let me look. Yeah, let me try that one more time. And then I'll pause the video if I just can't get this. 1,000 minus 636 times 0.244 times 25037. That looks right. Uh, 200 squared divided by 2. 20,000. Okay. Add to that is 2, 2, 2, 7. No, 1 too many zeros. Maybe that's it. Multiply by 2. Square root. Alright, that looks better. I just had 1 too many zeros. I bet that's what I did. Sorry about that. I'm sure it's not the most interesting thing to watch me do. But it does, and this is the reason when we do this in class, I have you guys do this along, and we operate by consensus. Right? We go until we agree upon a value. Now this is what the solutions from this particular version of the text gives us. It said that for this problem they found T2 to be about 636 Rankine. Hey, that sounds familiar. And just under 2120 feet per second, which is basically roughly what we found. So that's perfectly acceptable solution to this problem. Okay. Now, as I mentioned, there's multiple ways to do this problem. Let's talk about another way we could possibly do this problem. Okay. Using variable specific heat. So remember that problem originally said, hey, use variable specific heat to find a solution to this problem. Well, variable specific heat, if we look at the tables, the ideal gas tables, so we do have property tables for ideal gases, and if you look at those, they give you this S degree value. So they give you, based on temperature, they do give you an H and a U value. But they also give you this S degree value. Right? Now that's very important to be aware of, is that S degree is not an S value. Right? S degree is not the same as an S value. What you can do with these S degree values is when we look at this equation where we say, well, we say that S2 minus S1, if we look at Gibbs equation, we say S2 minus S1, and let's look at this version of the Gibbs equation. We say it's equal to this integral, minus R ln P2 over P1. And we say, well, it's normally approximately equal to the specific heat if it's constant. But if I use variable specific heat, I don't have to assume constant specific heat. I can say, well, this is equal to S degree 2 minus S degree 1. I call it degree. You could call it circle. I don't know what you want to call it. Minus then R ln P2 over P1. And these are table properties. Right? I just need temperature, and I can go look up these table properties. And I'm going to have to stop there. I'll pick up the next video. But that's what we're going to do. Let's look at that.